People always think we're attacking NASA, and we're actually NASA enthusiasts when it comes right down to it, right? We're space enthusiasts. We want accountability. We want disclosure. We want to see what's actually there, and we will accept the limitation. We'll support the limitations on what's capable of doing. We don't need to keep researching in and find out, oh, all we're looking at is CGI. If you can't do it, say so.
You have some as well, Robert. You have some material as well you'd like to present.
Well, I would like to show some of these films that I took out of the vacuum chamber. I'll explain what I did. The first thing I did was I took 2 rolls of film. Now, I got it from a factory in Hollywood. I got a pretty good deal on it. I purchased about 10 rolls of film, and it was the S-Star base, and it was the 2000 series. I took one of those films, put it in the camera, took the pictures. Then I took the control roll and took the pictures. And then I put the first one in the vacuum chamber, and I kept the control roll out. So then what happens when the pictures were all taken on both films, then I placed one of them in the vacuum chamber. And what I did was the very first test, I put a heat lamp to mimic the radiation from the sun. That destroyed the lid of the chamber, so I had to go get another one because the vacuum, it got too hot and the vacuum was sucking the lid in, so it was all warped and I couldn't seal it. So I went and purchased another chamber, a bigger one. With this experiment, what happened was when I developed both rolls at the same time in the same tank so that nobody could say, well, you developed them separately, you're going to get a separate result. I didn't want that to happen. And what I did was I put the camera on and I had it aimed at the developing system so that Scott could see the whole process being done. And what I would do is I would take the temperature and I'd bring the gauge up to Scott and I would quickly show him, okay, you see it's right there. It's sitting exactly where it's supposed to be. Anyway, so all this said and done, the very first set of films that came out, we compared them. And I have a little box that takes the pictures, so I can roll it through the box and it will go frame by frame, so I can take the pictures and then put them digitally in the computer and edit them. So I can put the 2 comparisons together. So you put 1 together, 2 together, 3 together. Now, on the black and white, the control roll came out beautifully. The one that was in that vacuum chamber under that heat lamp, it was completely fogged out. And this is only at a vacuum level of just maybe even scratching toward 10 to the -3, just maybe a little below that even. I did the same thing with the color, the S-Star Ektachrome 100. Now that was about the closest I could get for the fine grains that NASA was using. Same base, and the only difference is the backing of the film. For example, you could use saran wrap, let's say, for the backing. It's just the plastic backing. The chemicals that are going into that emulsion, they're all the same. They have to be, or you would not get a picture in the end. I did the exact same thing with the color film, only it didn't fog. The color film, all the hues went crazy. The blues were bleeding into the reds, the green was bleeding into the blues, and all the mountains were just blued right out. And the same with the grass. The grass was all bluish, really far off. And we've displayed that on several videos. And now we get to the third experiment where I did not use a heat lamp. And the same thing happened again, but this time I tested it with the black and white. And again, it was fogged. The control was okay, and the experimental one was fogged. It was actually the black and whites that were the worst. And this time, I wanted to see what it would be like when I put it by the microwave oven and give that film roll a 1-second burst with the door open. So I poked 2 chopsticks into the door switches so that I could keep the door open with the magnetron running. What had happened was when I did the control, And then I did the one that I zapped with the microwave oven, just sitting it on the outside. And it's only about an inch away from the door, with the doors open. So when I developed that, the film is all green. It's warped. The pictures are twisted. It's the strangest thing that I've ever seen. And it's all green. It has a really greenish haze to it. So what I'm saying is this. How can you get pristine photographs like that when you're in an environment that's torr 10 to the minus 11, which would be found on the moon? No fogging, nothing like that, when we only did it at just a shy below torr 10 to the minus 3. And look what happened. See, we had the hues go crazy, the colors went wonky, the film itself was fogged. The color wasn't as bad as the black and white, but it did fog. But all of the black and whites fogged.
Yeah.
You could see that right in the actual film negative itself.
It shows that vacuum it is bad for film. And of course, modern astronauts will use a digital camera. They have like special computerized digital cameras, just similar to the ones that we use, but they may be specially designed. At the time of the Apollo missions in the late 1960s and early 70s, they were using literally film cameras. Anyone younger than me wonders what that is. It's basically you used to put reels in things in it and wind them on and stuff like that. It was just like pieces of plastic that you wrapped around. And it's important to realise, because a lot of people jump in and say, well, NASA had their own special film. They didn't. J.P. Douglas Arnold, who was he worked for Kodak UK, has confirmed that. He said, and he was very close to the space program. He worked closely with them. He's an astrophotographer, a friend of Patrick Moore's, and he said that they actually used an off-the-shelf batch of Kodak Ektachrome. The only difference was they used the thinnest one they could find, because they wanted to get as many shots as possible, but it was something that was commercially available at the time. It was not developed especially for NASA and the space program.
When you go to March to the moon, like Scott and I have gone there many times to look, and I've showed this in many videos, is that when you go to March to the moon and you look in the description for each one of those film magazines that were taken, it shows you the panchromatic film, the high-altitude film. It gives you the numbers, the ASA number. It gives you everything that you need to know in there. And not one single one of those films that were in that list had radiation protection on them. Not one of them. And the last point that I would like to make is that Tim Trumbull is a friend of ours who lives in Australia. He worked on the Oxbury optical printer for 30 years, developing the film, making the special effects, setting all that up. Long story short, his film stock was starting to get fogged for some reason. So what had happened was he had called a scientist in from Kodak Labs, and they went through this problem and they tried to figure out, why is this film fogging? So they had figured it out that it was from the cosmic radiation that was coming through the Van Allen belts, and what was ever making it through was coming to the surface, and it was interfering with that film. So what they did was constructed a Faraday cage, and that's where Tim stored all of his film stock, and he never had a problem after that. So once again, when you are seeing these films being taken through the Van Allen belts all the way to the moon, pictures taken, video, whatever, and then they come back and you don't have any fogging, why would he have to build a Faraday cage for this problem when he's down here on the Earth? There's another problem.
You know that, of course, like, to experiment with the microwave oven is also an attempt to reproduce some of the effects of being on the moon, because it's not just the vacuum that's the problem. It's a very high radiation environment. There's the sun, which is producing a huge amount of radiation on all wavelengths, all frequencies, and very high amplitudes. In other words, for example, the light from the sun is like, I think it's 20% brighter because there's no atmosphere.
I have the documents on that.
Sure, thanks.
It's 56% brighter.
Even more, 56%.
You have 93% more UV radiation and about 54% more ultraviolet radiation.
Boy,
Plus you have the full spectrum of that radiation field that the sun is giving off.
Yeah.
One of the biggest things that they're talking about is they think, oh, they just brought the film out and took the pictures on the moon, And that's the only time that it's being fully protected. No, these magazines were not. As a matter of fact, the magazines that were on the outside of the spacecraft on the service module, other magazines were stored in the LEM for their ground photographs. They were already stored in Quadrant 1. They went through full launch. They're physically outside. They have no vacuum protection, no radiation protection, nothing for the entire trip. Then, when they go out and do an EVA, it doesn't matter where they store the film because they leave the door open. The LEM is not pressurized while they're gone.
Exactly, and the camera was a Hasselblad camera, which was specially designed for the space program, but it was not pressurized. It was not a pressurized camera like the one the spy satellites used. To come back to the sunlight. If the sun is 56% brighter on the moon, right, your eyes would be damaged. I mean, just the light alone, you'd need some kind of protection, and you don't often see the astronauts' faces dark.
That's why they have a gold shield over top of them, and if they needed to have that for their eyes, why did they not have a specialized lens for the cameras?
Yeah, the lens was normal. As you said, it's not just the light, it's the harmful rays, such as ultraviolet, which is filtered out by the Earth's atmosphere to the greatest extent. If it didn't, it could cause cataracts and other things that could blind you and do permanent damage to your eyes. Well, you mentioned the service module. I noticed that the film in the service module has to be brought back to the command module by an EVA in a spacesuit, because there's no way to access that compartment from inside the command module, inside the spaceship. You have to leave. You basically have to go around the outside to pick it up.
They only did that one time, and that's just before they so-called returned. Of course, none of it really happened. It's just part of the storyboard. It is a wonderful fairy tale. All of this stuff has been made up in advance, and they are changing it at will. They're changing it constantly. Over 50 years, they've had to keep changing this stuff.
Robert has just shown us an image of the electromagnetic spectrum, and it's the amplitude of the waves, in other words, how bright they are. What we should do is explain something about the units of measure we're using and about the scale, because vacuum is basically an absence of material.
Absolutely. So when you take it and you see a comment, like we have under the latest video, we have a comment from this gentleman, and he's talking about, oh, it's just this, there's no force. As the vacuum comes down, the force and force and force diminishes. So vacuum is not a problem. And there's only 3.7 psi in the suit. Well, I did the calculations for the suit.
Mike H. is a commenter, a YouTube commenter, I believe.
He's only looking at one side of the scenario, because you have the spacesuit is a wall between where you have an atmosphere and the outside where you don't. Then he refers to being pressure underwater. Well, to simplify it easily, when you go underwater and you're in a submarine or even in a suit or whatever, or a pressure suit under there, you equalize the pressure inside the craft to match the outside pressure of the water. However, the point being is that when you have pressure on the inside and pressure on the outside and you equalize those, there's no pressure on the hull itself.
That's right, yeah.
And what these guys say, oh, there's no pressure, there's only like 3.7 psi. But that's per square inch. PSI, per square inch. So 100 square inches of material has, at 3.7 per square inch, is 370 pounds. But what they don't understand is that's on the inside of the suit. On the outside of the suit, you have nothing. There's the two calculations that I did. So if you're inside of a spacesuit, which is approximately 2 square yards, not included the helmet, gloves, or boots, right? You have about 2 square yards of material. You now have 19,180 pounds. So when you take a look at the other calculator that I sent, that's what's on the outside pushing back against the suit.
Which is tiny. It's a tiny amount.
Yes. 1/5,000th of a percent. That's calculated at a torr value of 10 to the minus 7. Not being on the surface of the moon. You just got to add 5 more zeros to that. That's how little pressure is pushing back. So now the suit itself now has to handle that force because it's not equal. This is what they don't understand. that zipper is going to tear wide open. It has 10 tons of force. Like when you see these comments like that are under our videos, and they're going, oh, well, that's nothing. There's very little pressure there at all. It has no pressure. But that's only one part of the equation. It's just showing pressure equals force over area. Right? So to get the force, you measure the pressure times the area.
100% vacuum would mean there are no particles present. Pressure zero.
Right. So that's on one side. But on the inside of the suit, you're going to take pressure and multiply it by the area, and that equals the force. And there's the calculation. That's how it's calculated. But you have to do both sides of the equation. You have to do the internal pressure per square inch and outside pressure per square inch. And people don't quite understand that. And then within the other little pieces I cut out here, if you're just looking through them, this particular one, you can have different gauges. If you take a pressure gauge to measure the tire pressure in your car or whatever, right? Put it on there, it's only measuring just the pressure inside the tire. It's not bidirectional. It doesn't give you the total force between the inside and outside, because it would then have to cancel the outside air pressure on it. But when you have a different gauge, a differential gauge, right, it shows you the difference between the outside and the inside pressure on there. That's the total pressure against the wall between the two, or lack of atmosphere.
So it'd be like if you have a pressure gauge and you pump your tyre up, you'd have to have a separate barometer to check what the current air pressure was at the moment, because the air pressure varies at the Earth's surface.
But you can buy a differential pressure gauge to show the total force that's applied against there. And then if you open the one just directly to the left of it, and I specifically did that under the specifications on how you calibrate the different ranges, whether it's going to be torr, milligrams, or PSI or whatever. Take a look at the bottom, the warning at the bottom.
Warning, exceeding the maximum pressure range will destroy the sensor.
That's for all of the particular gauges, because they can only read to a certain pressure.
That's
then you have to use a mass spectrometer to read farther, where it's estimating the residual molecules in the vacuum. People say it doesn't have a force. They continue to do that. When you do the calculation, it is pressure equals force over area, right? It's always a force. People don't understand it's a force, and it's a magnificent force at that. There's so many examples on how to do that. Mythbusters, they used a shot vac. They picked 2 tons up, 4,000 pounds off the ground. They picked a pickup truck off the ground with a shot vac. They're only talking about a differential of maybe 1.5 pounds pressure in the atmosphere. Like you're taking probably the best shot vac will pull down from 760 torr down to 600 torr. The vacuum did not collapse. The machine didn't collapse. But when you put it over the surface area, you're able to pick the entire truck up. Well, that's the same as the surface area inside the spacesuit. Do you think a zipper can hold that much pressure?
Robert was mentioning the experiment he did with the film, coming back to that because it's related to a vacuum. It surprised me when I first heard about it, Scott, but there seems to be like a considerable difference in terms of the pressure variation you talk about. There's a considerable distance depending on how hard the vacuum is. So, for example, a vacuum chamber, like the one that Robert used, the pressure differential is very different in there than it is on the moon, where the vacuum is much harder. There's far less material.
We have Bill Demos working right now with his vacuum chamber at the university. We'll probably be getting some results probably next week or something, because he has the film once again in a vacuum chamber. A roughing vacuum is basically what Robert has, right? That chamber comes down equal to, say, 50 to 60 miles off the surface of the Earth. All right, you're still actually in the atmosphere. That's as far as it can pull it down. When you get these turbine vacuums that pull it down past that, and even Bill said to me, he said, when you get past 10 to the minus 4, he said, things start to happen that you had no idea would happen. because you're now affecting the molecular structure of materials. I mean, even steel. I have documents on the vacuums that show at what torr level the different materials off-gas at. And it's pretty amazing. Most of them start at 10 to the minus 3. That's in solid
I've
metal.
repeatedly shown that video of that fella doing exactly that, putting two metal discs together and using a rough-in pump. And look what happened. They stuck together.
You can do it even with that. You realize everything off-gases, even on Earth.
Liquid within a structure will actually evaporate in vacuum, yeah, that's off-gassing.
Everything off-gases at a different rate. The vacuum just simply speeds it up.
So here's the other thing that we were talking about too, is that with the Gateway project, those tubes are going to have structure, and really good structure built into them, with cross members or something that is going to hold that open from exploding. It's going to have to be contained because the ISS is only about torr 10 to the minus 6. And look at the structure that is on the inside of those modules. Now let's take that and go even further, and let's take that and build that around the moon's vicinity. Now it's going to be torr 10 to the minus 11. So the structure that's going to be required in order to contain that 1 atmosphere that they are claiming to put inside of this thing, it's going to explode as soon as they pressurize it, if it is not structurally sound. And the other thing is, they're only going to be able to use one-time seals. So that means that every time they dock and undock, before they can dock again, they're going to need metal seals, disposable metal seals that can be replaced each time. Because when we look at Bill's vacuum chamber that goes down to a torr 10 to the minus 6, every time he changes or replaces one of those little glass viewing ports and changes it to something else, or opens the lid to put something new into it, that metal seal has to be replaced because it gets crushed when you screw them down together in the plates between the two surfaces. So that would mean that if he has to do that down here on the Earth in 10 to the minus 6, that just imagine what that's going to be like when you get out to the vicinity of the moon at torr 10 to the minus 11. No structure, no go.
Yeah, this is important for listeners to realize that that the kind of effects that Robert has achieved with his experiments would be exaggerated many-fold on the moon, where the vacuum is much higher, much harder. There's far less material. It's like almost a pure vacuum, almost like deep space, rather than what you have, because the International Space Station is supposedly in space. It's in orbit, but there's still residual atmosphere at the altitude that it orbits, which is 200 odd miles. There's still residual atmosphere, which, as we've demonstrated, has an effect. When you reduce that effect, it feels like there's like a logarithmic rise in these vacuum effects. That's what it appears to be.
And then you look at the ones on the ISS. Now we're talking about the suits. If you compare those to the ones that were in the Apollo era, you notice that the suits on the ISS, they have structure to them. They're hard, the structure. Now, when you take the ones that were used on Apollo, they're quite flimsy. There's no structure to the suit. So how is that going to function when you get to torr 10 to the minus 11 in a flimsy suit, when these astronauts at the ISS, when they do a spacewalk, they're in an environment of torr 10 to the minus 6, and they have to have structure to that suit. And yet they're trying to tell us that the Apollo spacesuits had no structure to them, and yet they functioned just fine. Now that's impossible.
Yeah.
That is, it's impossible.
If you go onto YouTube, you'll find some videos of astronauts on the International Space Station and the Mir and the Space Shuttle actually dressing in their spacesuits. And there is a structure that it appears the chest part is rigid, and there's some kind of seal where the waist is. So the waistband is actually like a vacuum seal with something you just attach and clip in, and it looks like it's metal. And of course, the gloves and the boots attached the same way. It appears that the suit is in those sort of structures, and the helmet, there's a net on the neck as well. That's on the ISS, not on the moon. I mean, and Marcus knows all about this. It's just another element of this issue I think the listener should realise, is that astronauts had to do this in the lunar module when they were standing on the moon. And then they had to take them off again afterwards. And there's not much room in there. Not much room to move around.
I think we demonstrated that when they were faking it in the photographs, Buzz Aldrin was right up against the door frame. That was just simply a hollow shell that was in there. All they needed was just the frame piece and the ladder to come down off of to do the simulation. They needed as much room as possible in there just to climb in and out with the PLSS on. There's no way that two people could have been in there with all of the equipment they claim to have had, and included the console, which is not in the photograph. It's simply not there. And when you see those things and you realize that this is not only how they practice it, this is how they did the final simulations.
I don't know if Jim Collier's still with us. He actually went to a LEM in a museum and was allowed to take measurements of the inside of the compartment, the pressure hull in the LEM ascent stage. And it's quite shocking when you see the results he got about how small that space is, even with the console there. Yeah.
But they also refused to allow him to measure the one hatch. Said enough of that, they won't bring it over, they won't lift them up, they just let him have a little quick shot inside, and that was it, right?
I've heard it's 32 inches square, that's what I've heard.
That's the one coming out. The top hatch is only 24.
Oh, blimey, that's nothing.
Apollo 15 did a stand-up EVA out the top hatch.
Really?
It's possible that the umbilical cord was long enough for him to be able to do that. He's supposed to be standing on the engine and do the stand-up EVA, because that one wasn't really a planned thing like that, and considering they didn't have any contingency for additional consumables, that would have meant that they would have had to repressurize one more time than they'd planned on. And they just don't have that extra amount of material with them. You don't see any adjustment in the oxygen tanks, fuel tanks, or anything else between Apollo 11 and 17. If you realize just for 17, it's not just the weight of the rover, but there's nearly 2,000 pounds of batteries that they would have to have.
Yep, they were on there for the moon for a lot longer. They'd have had to have extra oxygen, extra scrubber material, which would be like to remove the carbon dioxide.
The EVA goes from 2.5 hours to 24 hours, so it's 10 times the consumables, just for the PLSs alone.
I've seen these scrubber material. I mean, I had to deal with this at the hospital because I had to change oxygen cylinders on machines, anaesthetic machines and things like that. Pressurize them and they don't last very long, and then of course you need scrubbers as well because some of the gases are rebreathed when you're in a hospital. You don't want to know about the details, and they have scrubbers to remove carbon dioxide and things like that when they're making the patient rebreathe the air. And these are like big plastic buckets full of white granules, and they change colour when they're chemically bonded with the carbon dioxide. And again, you need a lot of that. And there wasn't a very big margin of error. I mean, we know this because when it all came out long after the moon mission supposedly happened, they found out that, what if something goes wrong with the LEM? How long would, say, Apollo 11 have to do the repairs to get back? If they could do the repairs, it may not be possible. How long will they have? They said, they only had about 2 hours extra oxygen, something like that. I think it was 2 hours, which means that if it took longer than 2 hours to fix the problem and get back up to the command module, they'd suffocate on the lunar surface.
Exactly, but they didn't have a larger tank when they all of a sudden stayed for 3 days for 15, 16, and 17.
These are just some of the issues we've come up with, and I mean, a lot of the people like Jarrell White and Marcus Allen and Bart Zabrell and the other people you may be familiar with, I've interviewed a couple of these guys. It's a multidisciplined task, but basically, I think we proved that it is essentially like a movie. It's been described as being like a movie, and it is. But you brought up another point, Scott, and again, mumbling did not allow you. He kept interrupting you and stopping you from speaking. But you were explaining how there would have been a problem with communication. Now, it's important to realise that literally there's been only the Apollo produced live television pictures from the moon, like motion pictures in electronic form, which went onto people's TV screens, apparently. That was never repeated, interestingly, until the most recent landing on Mars, where for the first time since then we had motion pictures from outer space. Not including the ISS, which is in orbit, but we actually had motion pictures from another planet because the craft that landed on Mars did send back like a quite sophisticated motion image of its landing.
We don't know how that was simulated. The movie studios do a much better job today. If you
Some people
realize
say that was fake as well, yeah, the Mars missions. I mean, Richard D. Hall's done a thing about that, yeah.
you have to ask the question, why does NASA have 21 movie production studios? They have the largest, most expensive, the most highest tech movie production studios in the world.
If they're going to that level of technology to produce film, or they've got something on the scale of Hollywood, then maybe they are making Hollywood quality movies. And of course, there still are. And even contemporary with Apollo, there were some very realistic films that were created to simulate an outer space environment, including 2001: A Space Odyssey, which came out in 1968, which shows spacecraft. It shows astronauts on the moon. It's very similar, actually, to what happened with Apollo. The technology was available to produce very, very high quality, believable motion pictures of astronauts in space on the moon, on the moon, on the moon, on the moon.